Hey everybody, this is Larry. This is me doing the 11th day of the September Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think, and let's get started on today's problem: maximum product subarray. Okay, so you just have to find the subarray that is the maximum. I think this is actually a recent problem, or a variation of this as a recent problem on the Leetcode contest where you have to find the longest positive value instead of maximum product. But I think that's the same idea, but maybe with a more maybe with an additional edge case. But the way that I would solve this is with dynamic programming. So there are a couple of concepts here to kind of go over. Is that if you have zero, then well, if you have zero, then the answer for that it has to divide the left and the right from that. So if you have multiple zeros, you just take the subset or the subarray and then do the max product there. And then the other concept that I would think about is, well, the greedy thing makes sense, right? Like if you have multiple I'm just trying to think whether it would overflow. That's why I looked at for a second. But in either case, yeah, you just take as many numbers as you can. But if you see a negative number, so what you want is a even number of negative numbers, right? Because then now you can do it. So you can actually solve this with dynamic programming. The states, I usually generally solve this with bottoms up, but I'm going to try to solve this. No, maybe I should still solve it bottoms up. Yeah. I think actually, okay, I'm going to practice solving this top down with dynamic programming, just for practice and to kind of illustrate the transition states a little bit better. Because I think in the last time I tried to solve this, it took way too long. Yeah. But basically, the idea is that, okay, if this is a positive number, then you just keep on going whatever streak you had. And if this is a negative number, you want to just only keep track of only the you want to only keep track of the best results only if you have even number of negatives, right? So okay, so I think the way that I would think about it is, okay, you have a for loop, right? So we want to be able to start from the left to the right at any given time to kind of look at the longest thing. So I would have a for loop that kicks off the array like this. So for index in range of n, of course we have to define n as equal to nums. In this case, we're going to go, okay, let's say we have a best result is equal to, I guess the other thing that I have to think about the base case is that actually it could be negative, right? Negative could be your biggest product, largest product. So that, like, if you have one negative number, then that would be your largest product. So let's set this to negative infinity. And then now we just do max is equal to max of best, and then we go, let's just go best starting from index or something like that, right? Naming is hard, so but that's how I would think about it. And the idea behind this function for the dynamic programming is that we want to get the best answer starting from this index, right? Though maybe I might think about this a little bit weird. I forgot a state, which is the number of even numbers, which is 0. Oh, sorry, number of negative numbers, which is 0, right? So count negative. Okay. Now we can figure out okay, if num sub index is equal to 0, then just return 0, because that's your base case. Or, well, actually we have to do if index is equal to n, we just return 1, because if we reach the end, then we just treat it like, you know, normal. Otherwise you do that, and then now we do the current best is equal to the numbers of index, and then now we have two choices, right? One is to return like this is the end of your index, right? Or this is the end of your maximum subproduct, so we can return the max of the best, or we return the best starting from index plus 1 and then count negative. Okay, I might have to change that. If num sub index is negative, we do count of negative increment by 1, right? But what we want to do is also notice that if we have even number of negatives, then it revert back to positive. So we want to actually just multiply by 2 so that it goes from 0 to 1 and so forth. And then from here, that should be good enough, right? I think. Let's run it real quick, and I know that I haven't done the memorization yet, don't worry. We'll get to it. Ooh. Oh. I guess maybe this shouldn't be 1. What should this be? So I got the base case wrong, which is why this is giving me an issue. Oh. This is num sub index times this. Oops. Didn't even do any. I forgot that one critical step. Okay, there we go. Yeah, so that's why you check your answers. But the reason is that this is basically the transition. I focused on transition, but I forgot about the cost. But basically, you take the current number and then you multiply by the rest of the subset, or you just take the number, right? Meaning that you end here. So that's kind of the recurrence here. And again, this is going to run exponential. Actually, is it going to run? No. So this is actually going to run n square, because you only branch out once, right? So it's going to be n square running time. So which is actually not that bad, but you could, you know, this is a really weird way of just writing a for loop, right? So how do we reduce to linear time? Well, we reduce it to linear time by using memorization. So I'm having some struggle talking because my neck is in deep pain, so I need to see a doctor. But so if you see me struggling with the talking, I apologize. But yeah, but now now we want to add memorization, right? Because now this is n squared, because this goes to I plus 1, and then it's just n squared. This is a very standard way of writing the for, or you could simplify that by using a for loop. But yeah, okay. And then now, yeah, we just have to memorize. And because we reduce count negative to be 0 and 1, and index is from 0 to n, we can create the state, right? Which is calculated is equal to force times 2 for in range of n, and calculated result is equal to I guess it doesn't matter because we're supposed to override it, right? And we'll go over the complexity in a quick second, but I guess we could cache it after this. If is calculated of index count negative, we return calculated result index count negative. So otherwise we want to do calculated result of index count negative is equal to best, return best. Also obviously we have to do this thing, but to make sure that it gets thing. So you may also wonder, so this should be good. Run it real quick. I guess I should have compared the running time, though for two cases it shouldn't be that different, right? And so maybe we just do a big number. I don't know what. Okay, let's just do a big case real quick just for testing the complexity. So this is 10, 20, 40, 80. Oops. 160, 240, 320, 400, right? So 400. Let's try. So, ooh. Oh yeah, we overflow. Whoops. But So we see that this is okay. This is in my test case, but we see that it takes 64 milliseconds. I don't know if this is actually going to work, but you see that it's a lot slower. But yeah, let's submit this. Oh no. Why is that? I did get a wrong answer. Oops. Daisies. It is true. Why does this return? Oh, it's because I'm dumb. So because one thing that I did was that I manipulated count negative from the input, so this changes this result, which is usually I don't write it explicitly anymore, but so that's just silly. Okay. Maybe input. It's just me being silly. So this is why practice helps, even if you've done it 1,000 times like I have, because. And maybe just test more cases, because I think we should have tested that one, to be honest. Oh, still wrong answer, but that's at least that was going to be a bug in either case. Let me just double check. Yep. Okay. Oh. I want. No, I'm just double checking. I was just double checking my count negative thing to make sure that it's still good. But I think we actually change it here. So the best for one step should be 3, and then it should be negative 3. So that should be okay. We don't do anything with this count negative, so I think I'm doing something. No, I think we do for caching purposes. I think that's why. But that's odd. Well, the beauty of having this is that now we can just print out the calculated results for debugging. Okay. Negative 3. Okay, I think my form is definitely way off. So on my recurrence, because looking forward, what happens is that this returns -1. Oh, sorry, this returns 1, but which is the max. But then this returns 1 instead of -1. I think my recurrence is wrong. what I needed to do is so this is actually a good example of something that you have to kind of check a little bit. But what I actually want to do is having different things. So basically, if count negative is equal to 1, then we actually want the minimal answer here. Or we want this to return the minimal answer. Right? Because we want the min as in the best negative answer, and not, you know, I think this should be right. But, ooh. Maybe not. Oh, this is, we confused the thing again. Okay. So yeah, let's try again. I'll explain in a second. Sorry. Okay, cool. Yeah, that's so that the beauty about dynamic programming or memorization is that once you get to you can mess up on transition and as long as you have the general right idea, it's easy to fix. And for me, the incorrect thing was mixing the min and the max, and it's because basically if your input, and I was wondering why I wasn't doing anything with the count negative other than caching, and the reason is because if the input is negative, that means that we want and I think if I were to rewrite it again, I would separate these two to two functions so that it's more clear. And in fact, yeah, I think that's my mistake. But because the best starting from depends on whether it's negative or not. Because if your suffix is, or if your current number is negative, right, which is, you know, our current number is here. If our current number is negative, then we want the min number from the rest of it, because whatever, you know, your best result is going to be the smallest number, whether that's negative or positive, times the current number, because then that gives you the max, right? So you have to think about it that way. Yeah, otherwise, so what is the complexity of this? Well, the number of possible inputs to index is going to be O of n, and or just n specific, n total, n plus 1. Count negative could only be positive or negative, so yeah, so that's only going to be 2. So you have O of n possible inputs to this, and because each of these only does O of 1 work, this is going to be a linear time algorithm. And as you can tell, it is going to be linear space because of how we store it. And in fact, you can actually do this in, because if you take a look at this, you only look at index plus 1. You can actually do this in constant space. And if you want to upsolve this, try doing this with bottoms-up dynamic programming and then converting with the O of 1 space algorithm. I'll put a link below on my kind of walkthrough on doing that. But yeah, that's all I have for this problem. I think this is a fun dynamic program problem, and I really should practice this more. But yeah, let me know what you think. Hit the like button, hit the subscribe button. Let me know your questions. I'm struggling a little bit today because of my neck issues, but yeah, let me know. Bye bye.